A tyre may perform perfectly on a paved road, but a military UGV rarely operates only on smooth and predictable surfaces. It may need to travel over loose sand, gravel, mud, steep slopes, and uneven obstacles. Each terrain behaves differently and changes how much traction the tyre can generate, how deeply it sinks, how much energy the vehicle consumes, and whether the vehicle can continue moving safely. This is why understanding terrain mobility is so important. In Part 4 of this training program, we will focus on how tyres interact with different terrains and how this interaction ultimately determines the real-world mobility of a UGV. Let us begin Part 4, Terrain Mobility. Welcome to Part 4 of our tyre training series, Terrain Mobility. In this video, we will begin with traction and wheel slip, understanding how effectively tyre torque is converted into useful forward motion. Second, we will examine rolling resistance and its effect on power consumption, speed, and vehicle range. Third, we will then explore different tread patterns and how they support performance across varied terrain. Fourth, we will look at inflation pressure and how it influences contact area, flotation, and tyre durability. Fifth, we will introduce TPMS and CTIS and understand how these systems help manage tyre pressure and monitor tyre health. Let us begin with traction and wheel slip. This image explains how a tyre converts motor torque into useful traction. Traction is the force generated at the tyre ground contact area. It allows a vehicle to accelerate, climb, brake, and steer. Without sufficient traction, the wheel may rotate, but the vehicle will not move effectively. On hard ground, traction is produced mainly through friction between the rubber and the surface. On loose terrain, the tread blocks must also engage with the soil. The tyre pushes the ground backward, and the ground reaction pushes the tyre, and therefore the vehicle moves forward. However, some wheel slip is necessary to generate traction on loose terrain. The goal is controlled slip. With good traction, most of the tyre's rotation becomes useful forward movement. With excessive slip, the wheels spin, energy is wasted, and the terrain is disturbed. This can reduce control and eventually immobilize the vehicle. Good traction is therefore essential for acceleration, slope climbing, braking, steering, and reliable mission performance. This image explains wheel slip, the difference between how far a tyre should travel based on its rotation and how far the vehicle actually moves. Some slip is normal, especially on loose terrain. With low or controlled slip, most of the tyre's rotation becomes useful forward motion. This provides good traction, better efficiency, and stable vehicle control. With high or excessive slip, the wheel spins faster than the vehicle advances. Energy is wasted, the terrain is disturbed, and the tyre may dig itself into a deeper rut, increasing the risk of immobilization. Wheel slip increases when the demanded tractive force is greater than the traction available from the terrain. Common causes include high torque, low friction, loose soil, sinkage, excessive load, and unsuitable tyre pressure. Managing wheel slip is therefore essential. Too much slip reduces traction, mobility, and steering control, while controlled slip helps the vehicle climb, accelerate, and move reliably across difficult terrain. This image explains how slip ratio affects torque transfer and usable traction. Slip ratio compares the distance suggested by wheel rotation with the actual distance traveled by the vehicle. At zero slip, the tyre rolls without spinning. As slip increases, more wheel rotation is lost and less becomes forward motion. On loose terrain, a small amount of controlled slip is often necessary to generate traction. Too little slip may produce limited tractive force, while excessive slip causes wheel spin, wasted power, and soil disturbance. The goal is to operate within the best traction zone. Motor torque twists the wheel and the tread pushes the terrain backward. In response, the terrain pushes the tyre forward, creating tractive force. On firm ground, more torque becomes useful vehicle movement. On soft ground, weak terrain support causes more torque to become sinkage and slip. Therefore, controlled slip helps maximize traction, climbing ability, efficiency, and steering control. The objective is not zero slip, but the right slip ratio for the terrain. We have now completed traction and wheel slip and understood how tyre torque is converted into useful forward motion. Next, let us look at rolling resistance, the force that opposes vehicle movement and directly influences power demand, efficiency, speed, and operating range. This image explains rolling resistance, the force that acts opposite to a tyre's direction of travel. As the tyre rolls, it continuously flexes while entering and leaving the contact patch. Because rubber does not recover all of its energy perfectly, some energy is converted into heat. This is called hysteresis loss. On soft terrain, additional energy is consumed as the tyre compresses the ground and creates a rut. This is why rolling resistance is normally lower on pavement and higher on sand, mud, and loose soil. Inflation pressure also matters. A tyre with excessively low pressure deforms more, creating greater energy loss and higher rolling resistance. For a vehicle, higher rolling resistance means greater motor torque and electrical power demand, more heat generation, and reduced battery range. Therefore, tyre pressure, vehicle load, and terrain must all be considered when estimating mobility and power requirements. This image explains the basic formula used to estimate rolling resistance. The equation is rolling resistance force equals the coefficient of rolling resistance multiplied by the normal load on the tyre. Here, FRR is the rolling resistance force, measured in newtons. It represents the force opposing the tyre's movement. CRR is the coefficient of rolling resistance. It depends on factors such as tread design and terrain condition. W is the normal load carried by the tyre, also measured in newtons. The relationship is straightforward. If the tyre load increases, rolling resistance increases. Similarly, a higher rolling resistance coefficient produces a greater opposing force. For example, when the coefficient is 0.04 and the normal load is 5,000 newtons, the rolling resistance force is 200 newtons. This coefficient is generally low on pavement and becomes higher on gravel, sand, mud, and soft soil. This image compares typical rolling resistance coefficient, or CRR's, values across different terrain types. On smooth asphalt and concrete, the coefficient is lowest because the surface is hard and the tyre experiences limited deformation. This means efficient rolling and lower power consumption. On gravel, hard soil, and grass, the coefficient increases as vibration, surface roughness, and terrain deformation become greater. Sand shows a much higher range because the tyre sinks and must continuously push loose material aside. Mud and soft soil can create even greater resistance due to deep sinkage, rut formation, and poor terrain support. Snow varies widely depending on its depth, temperature, and level of compaction. Firm packed snow may offer moderate resistance, while deep loose snow creates much higher losses. These values are approximate and must be adjusted for tyre type, inflation pressure, wheel load, speed, and actual terrain condition. The formula remains resistance force equals CRR multiplied by the normal load. Therefore, a higher coefficient directly increases the tractive force and power required from the vehicle. This image explains how rolling resistance behaves when a vehicle travels on a slope. In the first section, the vehicle's weight is divided into two components. The normal component, W cosine theta, acts into the slope and determines rolling resistance. The downhill component, W sine theta, creates the grade force. As the slope becomes steeper, rolling resistance decreases slightly, but the grade force increases rapidly and becomes dominant. The second section shows uphill travel. Both rolling resistance and gravity act against the direction of motion. The motor must overcome their combined force. With a rolling resistance coefficient of 0.04, total resistance rises from approximately 21% of vehicle weight at 10 degrees to more than 53% at 30 degrees. The third section shows downhill travel. Rolling resistance still opposes motion, but gravity now assists the vehicle. When gravity becomes greater than rolling resistance, the vehicle accelerates unless the brakes or regenerative system control its speed. The key takeaway is that gradient changes the total tractive force and braking requirement far more than it changes rolling resistance itself. We have now completed rolling resistance and understood how it influences the vehicle's power demand, efficiency, and operating range. Next, let us look at tread patterns, how different tread elements and designs provide the grip, self-cleaning, and terrain performance required for each mission. Here we will see 5 major tire tread categories and shows why tread selection must match the operating terrain. First is the highway terrain tire, or HT. Its continuous ribs provide quiet operation, long tread life, and low rolling resistance on asphalt and concrete. However, it offers limited traction in mud, sand, and demanding off-road conditions. Second is the all-terrain tire, or AT. It balances road comfort with off-road capability, making it suitable for gravel, hard soil, and mixed military patrol routes. It is versatile and durable, but not ideal for deep mud or loose sand. Third is the mud terrain tire, or MT. Its large, widely spaced tread blocks bite into mud, clay, and soft soil while clearing material from the tread. It provides strong traction and side grip, but creates more noise, wear, and rolling resistance on roads. Fourth is the sand terrain tire. Its broad pattern is designed to improve flotation and reduce sinkage in dunes and loose sand. It performs well at speed in desert conditions, but offers weaker grip in mud, rocks, and hard terrain. Finally, the snow or winter tire, identified by the 3PMSF marking, uses fine sibes and flexible rubber for traction on snow and ice. It performs best in cold conditions, but wears faster and creates more resistance in warm weather. The key lesson is simple. No tread pattern is best everywhere. The correct tire must be selected for the vehicle's primary terrain and mission. This image explains how tread design influences tire performance and how the correct pattern should be matched to the terrain. First, the void ratio is the amount of open space between the tread blocks. A low void ratio provides more rubber contact with the road, resulting in lower noise, longer tread life, and better efficiency. A high void ratio provides larger open channels, improving mud evacuation, self-cleaning, and traction on loose terrain. Second is self-cleaning capability. When mud remains trapped inside the grooves, the tread surface becomes smooth and traction decreases. A well-designed open tread flexes and ejects the trapped soil as the tire rotates, keeping the grooves clear and maintaining grip. This image explains 4 important elements of a tire tread pattern and how each contributes to mobility. First are the tread blocks. These are the raised rubber sections that directly contact the ground. They generate traction for acceleration, braking, and climbing. Larger blocks generally provide better durability and grip on rocks, while smaller blocks offer a smoother and quieter ride. Second are the grooves, which are the channels between the tread blocks. Their main purpose is to evacuate water, mud, sand, and snow. Deeper and wider grooves improve clearing and help the tread remain effective in difficult conditions. Third are the void spaces or the open areas within the tread. A higher void ratio improves self-cleaning and traction in mud and soft soil by preventing debris from packing between the blocks. A lower void ratio places more rubber on the road and is generally better for paved surfaces. Finally, we have the shoulder lugs, located near the outer edges of the tyre. These aggressive blocks improve side traction, cornering, rut climbing, and side slope mobility. More open and aggressive shoulder lugs usually provide better off-road grip and self-cleaning. In this image, we explain 4 additional tread features that improve tyre stability, grip, protection, and durability. First are the center ribs. These are continuous tread sections running around the middle of the tyre. They improve straight-line stability, steering response and highway handling, while also reducing rolling resistance and irregular wear. Wider or additional center ribs generally improve road performance. Second are the sipes, small cuts within the tread blocks. These create extra biting edges and provide micro grip on wet, snowy, and icy surfaces. They also improve braking on slippery terrain. More or deeper sipes can increase grip, although excessive flexibility may increase tread wear. Third are the stone ejectors. These are small rubber protrusions positioned inside the grooves. Their role is to prevent stones from remaining trapped in the tread. This reduces puncture risk, limits groove damage, and helps maintain traction on rocky terrain. Finally, tie bars are rubber bridges connecting adjacent tread blocks. They reduce excessive block movement, improve high-speed stability, and help prevent irregular wear. They can also increase tread durability and load-carrying strength. Together, these features fine-tune tyre behavior for stability, surface grip, damage resistance, and long-term performance. This image shows how different tread elements are combined to create tyres for specific operating conditions. First is the mud terrain tyre, or MT. It uses large tread blocks, deep grooves, and a high void ratio. Aggressive shoulder lugs provide strong side grip, while the open pattern allows mud and soft soil to escape. This design is best suited for mud, clay, forest trails, and other soft terrain. Next is the all-terrain tyre, or AT. It combines medium-sized blocks, moderate grooves, and a medium void ratio. Functional shoulder lugs and partial center ribs provide a balance between off-road traction and on-road stability. This makes it suitable for mixed terrain, gravel, hard soil, and military patrol routes. Finally, the highway terrain tyre, or HT, uses smaller blocks, shallow grooves, and a low void ratio. Continuous center ribs improve straight-line stability, reduce noise, and support efficient, high-speed travel. The key takeaway is that tread patterns are created by combining different elements. More open and aggressive patterns favour off-road traction, while tighter patterns favour road comfort, efficiency, and stability. We have now completed tread patterns and understood how tread elements are selected for different terrains and mission requirements. Next, let us look at inflation pressure, how tyre pressure affects the contact patch, flotation, traction, ride comfort, heat generation, and tyre durability. This image explains what PSI means and how tyre pressure supports a vehicle. PSI stands for pounds per square inch. It is a unit used to measure the air pressure inside a tyre. For example, a tyre inflated to 40 psi has approximately 40 pounds of force acting on every square inch of its internal surface. The arrows inside the tyre show that air pressure acts in all directions. This pressurized air pushes outward against the tyre structure and allows the tyre to maintain its shape. The second section explains who actually carries the vehicle's weight. In a pneumatic tyre, most of the load is supported by the pressurized air inside the tyre. The rubber, belts and sidewalls contain that air and transfer the load safely to the ground. Therefore, correct inflation pressure is essential. Too little pressure causes excessive deformation, while too much pressure reduces the contact patch and can affect traction, comfort and durability. This image explains how inflation pressure affects the tyre's contact patch and ground pressure. In the first section, higher PSI makes the tyre stiffer. It deflects less under load, creating a smaller contact patch. This is useful on hard roads, but it concentrates the vehicle load over a smaller area. Lower PSI allows the tyre to deform more. The contact patch becomes larger and spreads the load across a wider area. The second section connects this to ground pressure, which is approximately vehicle weight divided by contact area. At high pressure, the smaller contact patch produces higher ground pressure. On soft terrain, this increases sinkage and can reduce mobility. At lower pressure, the larger contact patch reduces ground pressure. This improves flotation, traction, and the vehicle's ability to travel over sand, mud, and loose soil. However, pressure must remain within approved tyre limits because excessive deflection can increase heat, sidewall stress, and tyre damage. This image shows how changing tyre pressure can significantly affect the mobility of the same vehicle. On the left, the tyre is inflated to 45 psi. The higher pressure makes the tyre stiffer and creates a smaller contact patch. This produces higher ground pressure and better rolling efficiency on paved roads. However, on sand or soft soil, the tyre is more likely to sink, reducing off-road mobility. On the right, the tyre is reduced to 20 psi. It deflects more and creates a larger contact patch. This spreads the vehicle load, lowers ground pressure, and improves flotation and traction on soft terrain. The table then connects tyre pressure with terrain. High pressure is generally suited to highways, medium pressure to gravel and hard soil, and lower pressure to mixed terrain and mud. Sand and snow may require very low pressure for better flotation. These figures are only typical strategies. The final pressure must always consider tyre limits, wheel load, speed, and the manufacturer's recommendations. We have now completed inflation pressure and understood how it affects traction, flotation, ride comfort, and tyre life. Next, let us look at TPMS and CTIS, systems that help adjust tyre pressure for changing terrain and continuously monitor tyre pressure and temperature. This image explains how a tyre pressure monitoring system, or TPMS, monitors tyre condition and communicates that information to the vehicle operator. On the left, we see the TPMS components installed at the wheel. A compact sensor module is normally mounted near the valve stem or inside the rim. It contains a pressure sensor, temperature sensor, battery, and wireless transmitter. The sensor continuously measures the air pressure and temperature inside the tyre. It then sends this information wirelessly from the rotating wheel to the vehicle. On the right, each wheel transmits its data to the TPMS receiver or electronic control unit. The system processes the readings and displays the pressure and temperature of every tyre on the dashboard. Normal readings are usually shown in green. When a tyre becomes underinflated, overheated, or develops a rapid pressure loss, the system highlights the affected wheel and activates a warning indicator. For a military vehicle, TPMS supports early leak detection, safer operation, longer tyre life, and reduced risk of unexpected tyre failure during a mission. This image shows the driver's view of a tyre pressure monitoring system, or TPMS, integrated into a military vehicle dashboard. At the center, the TPMS display presents the pressure and temperature of every tyre individually. Green readings indicate that the tyres are operating within the normal range, allowing the driver to verify the complete vehicle at a glance. The system status panel confirms whether the tyres are healthy, temperatures are acceptable, and all wireless sensors are connected. Below the main display are the three critical alert types: low pressure, high temperature, and rapid air leakage. When a problem occurs, the affected tyre is highlighted in yellow or red, depending on the severity. The operator should continuously monitor these readings, investigate warnings, and stop the vehicle if a critical condition develops. Where CTIS is also installed, tyre pressure may then be adjusted from inside the vehicle. TPMS does not normally control tyre pressure itself. Its role is to detect developing problems early, improve safety, protect the tyres, and reduce the risk of mission failure. This image explains how a central tyre inflation system, or CTIS, adjusts tyre pressure directly from inside the vehicle. The left side shows CTIS at the wheel. Air travels through a pressure line into a rotary union at the wheel hub. This rotary union allows air to pass into the tyre even while the wheel is rotating. Valves and pressure sensors control and measure the airflow, allowing the tyre to be inflated or deflated without stopping for manual adjustment. The right side shows the system inside the vehicle. An air compressor generates compressed air and stores it in a reservoir. The CTIS controller receives the operator's selected terrain mode, such as highway, gravel, mud, or sand, and commands the valve manifold. The manifold then distributes air through pressure lines to each wheel. The system can increase tyre pressure for hard road efficiency or reduce it to enlarge the contact patch on soft terrain. This improves traction, flotation, and mobility, reduces ground pressure, and allows the vehicle to adapt quickly as terrain conditions change. This image shows the driver's view of a central tyre inflation system, or CTIS, integrated into the vehicle dashboard. At the centre is the CTIS control panel. The operator first selects a terrain mode, such as highway, gravel, mud, or sand. The system then identifies the appropriate tyre pressure setting for that operating condition. The tyre pressure display shows the current PSI for each wheel, allowing the operator to confirm that all tyres are correctly inflated. The inflate and deflate controls can be used to manually increase or decrease tyre pressure when required. Below them, the panel displays compressor status, system air pressure, and overall air system condition. Warning indicators alert the operator to low tyre pressure or a possible system fault. Before moving, the operator should select the correct terrain mode, allow the system to complete the pressure adjustment, verify all tyre readings, and check for warnings. This interface allows tyre pressure to be managed without leaving the vehicle, improving mobility, safety, and mission efficiency. That brings us to the end of Part 4 of our tyre training series, Terrain Mobility. In this video, we explored traction and wheel slip, rolling resistance, and different tread patterns and how they are matched to specific terrain conditions. We also got introduced CTIS and TPMS, which help adjust tyre pressure and monitor tyre condition. We hope you found this video useful. Thank you for watching, and we will see you in the next video.